let's discuss this case. Like we have discussed case 1 and case 2 in previous video. So now we'll discuss the second case of master theorem. So when we have a recurrence relation of the form T of n equal to a T of n by b plus f of n, and the C critical value which we have calculated is log of a to the base b, and the value of C will be obtained by representing f of n in the form of big O of n to the power C. So n to the power C, and that C represents the value of C. And the case 2 of Master's theorem is when C equal to C critical, we will have case number 2. Now under this case 2 we have 3 sub cases, that is 2a, I'll just write here 2b and then 2c. Now what are these sub cases? Now let's say we have f of n. Now like f of n, instead of representing only big O of n to the power c, instead of representing it as a n to the power c, we can represent it also as n to the power c log n to the power k. So let's say I'll take some examples of f of n. If f of n equal to n, what will happen? If f of n equal to n, we'll be getting, we will represent it of this form. It is it is big O of n, right? As per observation we can write it as a big O of n, but we can just make some arrangement in the same big O of n to the power 1, right? And log of n to the power 0. So any term power 0 is 1. So this term is 1 and n to the power 1 is like only n. So we will get big O of n. So now by looking at this, we will get C equal to 1 and k equal to 0. What if I have f of n equal to n log of n? Then it is C equal to 1 and k equal to 1. What if n by log n? Then we will have big O of n log of n, and this has a power minus 1, which is k equal to minus 1 and c equal to 1. So instead of representing f of n just as a big O of n, we have to represent it of the form n to the power c log of n to the power k. So based on this value of k, now what is k? So whatever k we have calculated in these cases, k equal to 0, 1, minus 1. So based on that value of k, we have 3 sub cases in Master's theorem. And when the case 2 holds, when we have C equal to C critical. So instead of this C, somewhere you may see as a C critical as well. So even f of n you can represent of the form big O of n to the power C critical and log of n to the power k. So anything may be there. So now if k is greater than or equal to, only if big K is greater than minus 1. What if K is greater than minus 1? So if K is greater than minus 1, we can represent the complexity as theta of n to the power C critical, theta of n to the power C critical log of n with power k plus 1. So if k is greater than minus 1. What if k equal to minus 1? Again it is same. It is theta of n to the power C critical. The only change will happen here, it is log of log n. Log of log n. If it is a k equal to minus 1. And what if we have k less than minus 1? So which is implying theta of n to the power C critical. So these are the 3 cases under the Master theorem of case 2. So 3 sub cases for case 2 which we have discussed for master theorem. So what is the case 2 now? The case 2 is whenever we have a C equal to C critical, then we have three cases. One case is K is greater than -1, K is equal to -1, and K is less than -1. If K is greater than -1, what we will be getting? N equal to the complexity of T of n is given as theta of n to the power C critical log of n to the power K plus 1. If it is -1, then theta of n to the power C critical log of log n, and if it is less than -1, theta of n to the power C critical. Now let's start with the examples. So we have example 1 as T of n equal to we'll write it as a 2T of n upon 2 plus n. So now again we have A equal to 2, B equal to 2. If you just compare with A, T of n by B plus f of n. And now if I write this f of n as f of n equal to n, which I can write as n to the power 1 log of n to the power 0. So I will be getting C equal to 1 and K equal to 0. So now as K equal to 0, that is K greater than -1. We got this case. So now how will I get we got K equal to 0, then we got C and C critical we have to calculate. C critical equal to first log of A to the base B, which is log of 2 to the base 2, which is equal to 1. So now we have the case C critical equal to C. So these two are equal, so it falls under the case 2, and under case 2 if we compare with this n to the power 1 log to the power 0 n, we get K equal to 0, and this falls under K greater than -1 category, where the complexity of T of n will be represented by theta of n to the power C critical log of n to the power K plus 1. And now what is K? We have 0 and C critical is 1, so we are getting complexity of the given function or complexity of given recurrence relation using Master's theorem is C critical is 1, so it is n, and K is 0, 0 plus 1, 1, so it is n log of n. So in previous some older videos where we tried to solve the recurrence relation, this recurrence relation we might have solved, and you can see that we got the same exact complexity as big O of n log n for this relation, which is directly solved. So this falls under case 2, and with case 2 of Master's theorem we don't need to solve it recursion tree also we don't need to draw, or we don't need to do the substitution. Just we have to identify under which case it falls, and based on that, using Master theorem, we can directly compute the complexity of it. So let's take all the three case examples here. So again I will write it like this: T of n, which is equal to 4T of n by 2 plus n square upon log of n. So now again compare A equal to 4, B equal to 2, and we have to calculate C critical. C critical equal to log of A to the base B, which is log of 4 to the base 2, which I will be getting as 2. Now when I have n square log n, I will represent f of n, which is n square log of n to the power minus 1. So now if I just say that it is n to the power C log of n to the power k, if I compare it, so I will be getting C equal to 2 and k equal to minus 1. So now when it comes to k equal to minus 1, it falls under second category, and another, if you just see C equal to C critical we got, because 2 is equal to 2. So now the k equal to minus 1 case, we have the complexity of T of n is given as theta of n to the power C critical into log of log n. So what is C critical now? 2. So we will be getting complexity of given recurrence relation using Master's theorem is n square log of log n. And the last case which we can again solve it in the same equation, or like, okay, let's take one more recurrence relation. T of n equal to 2t of n by 2 plus n upon log n square. So I have again, I'll just take it a little bit faster. A equal to 2, b equal to 2, then we got c equal to 1 and k equal to minus 2. So log square n, I will just write it log to the power minus 2n as a term in the numerator here. So we got a equal to 2, b equal to 2, c equal to 1 and k equal to 2. So now c critical, if we compute, we will be getting log of a to the base b, which is equal to log of 2 to the base 2 will give you 1. So we got c equal to c critical equal to c, which is, and k equal to minus 2, so which falls under the category k less than minus 1. So if k is less than minus 1, then we have complexity of T of n with our, you can just see here which we have written the cases. So this case we have discussed, this case we have discussed, and last case complexity of T of n is theta of n to the power c critical. So now we have theta of n to the power c critical. So you can see that now it is theta of n because c critical equal to 1. Instead, if I could have another possibility in this equation is 4 and I can make it n square, then this could be theta of n square if I would have done these two changes. Okay, thank you.